Hello students, welcome to Sri Jendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 4 of a unit Nuclei. So let's begin with today's session. In today's session, first we are going to discuss about the Q value of the reactions. So let's have a look. What is the Q value? Basically, that is the energy released in any nuclear reaction where Q value could be calculated as a delta m into c square, where delta m is in kg and delta m is the mass defect in nuclear reaction. So this Q value will be equals to delta m multiplied by 931.5 MeV if delta m is in the atomic mass unit. So this delta m would be equals to mass of the reactants minus mass of the products. So if mass of the reactants is greater than the mass of the products, then the Q is greater than 0 and the total amount of energy is going to release, and this reaction is known as the exothermic. If mass of the reactants is less than the mass of the product, then the Q will be less than 0 and energy is absorbed. And if energy is absorbed, this reaction is considered as the endothermic. Examples of exothermic reactions are the nuclear fission and nuclear fusion. An example for endothermic reactions are such as, let's say it's a 7 and 14, it's a nitrogen plus helium, it's a 2He4, that will give me an oxygen plus 1H1. Yes, and in exothermic reaction, the total binding energy of the product in exothermic reaction, the total binding energy of the product will be greater than the total binding energy of the reactants, while in the case of the endothermic reactions, the total binding energy of the product will be less than the total binding energy of the reactants. So in terms of the binding energy, the energy released in a nuclear reaction can be given as a Q value would be equals to binding energy of products minus binding energy of reactants. So now let's look at one of the numerical and the things will be more clearer. So suppose I have been asked that calculate the energy released in the following reaction, and reaction is given such as it's 3Li6 plus 0 and 1 will give me it's a 2He4 plus 1H3, and they have given that mass of 3Li6 is 6.0151 AMU. Mass of the 1H3, so mass of the 1H3 it's a 3.0160 AMU. Mass of the 2He4, it is the 4.0026 AMU. Then they have given the mass of the 0 and 1, which is 1.0086 AMU. So this is the data that has been given. Their masses are given and the process is given. I need to find out the energy released in the following products and the following relations. So what I understand is that the energy release will be equals to mass of the total mass of the reactants minus total mass of the products. Basically it is something like this. This Q is equals to delta m into c square. So let's see the total mass of reactants and that would be approximately, it says, if you add this, it's a 7.0237 AMU. Same way, total mass of products, that is approximately equals to 7.0186 AMU. Then the difference, it's a delta M, which is equals to, if you subtract this, and that means mass, total mass of reactants minus total mass of products, you are going to have this, it's a 0.005138 AMU. And this energy released, that is equals to delta M into C square. This delta M into C square, this is equals to 7.0186 multiplied by 931.5 MeV. This is 4.783 MeV. This would be the answer. What was yours? Yes, this is just the calculative question, but we must understand that even this can be asked, and they have asked this several times. I hope this is clear. Is it clear? Is it? Are you sure? So do you have any doubts on this? Is there anything? No? Great. Let's look at one more question like this. They said that the binding energy, per nucleon for deuteron is x1, and for alpha particle per nucleon is x2. The energy released, in the given relation is, and the relation is given, that is 1h2 plus 1h2 will give me 2He4 plus Q value. So if you want to calculate this Q value, what you need to do is that you simply need this, it's a Q would be equals to, it is the binding energy of this 1h2 plus binding energy of this 1h2 minus binding energy of 2He4. As you have already written binding energy, no need to write down multiplied by C square. I hope this is clear. Is it clear? Yes. So what the data is given, it's a binding energy per nucleon. Please have a look at this. Per nucleon for deuteron is x1. So that means it's a binding energy for deuteron is 2x1. I hope this is clear. Binding energy for deuteron is 2x1, and we have two deuterons, so it's a 2x1 plus 2x1. Yes. And same way, binding energy for alpha particle is, it's a 4x2 because it's a 2He4. Yes, 4 multiplied by x2. So this Q value would be equals to 2x1 plus 2x1, because look at this, this is one deuteron, this is second deuteron, minus of this, minus of 4 into x2. So this is simply the 4x1 minus of 4x2, or you can simplify this such as 4 into x1 minus x2. This is the Q value of this kind of relations. I hope this is clear. Is it clear? So now do you have any doubts in this? Is there anything? Is there? No? Great. So now let's switch to the radioactivity. The nuclei having large number of masses are highly unstable and that disintegrate spontaneously by emission of radiations, whether it could be an alpha or beta or a gamma, and this is called as the natural radioactivity. So when a nuclei decays, it can emit particles or photons. The decay products were originally called as the alpha, beta and gamma. And in general, natural radioactivity takes place is heavy nuclei beyond late in periodic table. So there are also natural radioactivity in light nuclei such as in potassium or in 6014 or in 37, it's a rubidium. Yes, so even but they are very rare. In general natural radioactivity takes place in all or in element which is heavy in nature. I hope this is clear. Yes. So now let's first discuss the decay of nuclei, that is the alpha, beta and gamma decay, and then we will switch to the laws and formulas of this. So let's first begin with the alpha decay, that how alpha particle is going to be decay. So let's begin with the alpha decay. So let's have a look that suppose we have a certain element that is the we have, let's say, 88 protons and 138 neutrons, and this is the element, it's a 88 R8 226. This is the parent nuclei, and from this parent nuclei an alpha particle is going to be emitted or decayed. When this is emitted or this is decayed, its atomic number would be decreased by 2 and its atomic mass would be atomic mass would be decreased by 4. So if it is 138 minus 2, that is the daughter nuclei should be having 136 neutrons, and as it has been reduced by 4 in atomic mass, so this would be equals to 226 and this should be equals to 222. I hope this is clear. So decay will follow the following pattern. Parent nuclei would be there. It will give us a daughter nuclei plus alpha particle, and this is what we call as an alpha decay. So an alpha particle is composed of two protons and two neutrons, and the alpha particles generally does not carry on electrons, so it has a charge of plus 2e. So emission of an alpha particle by a nucleus to transform it into a different nuclei is called as the alpha nucleus, and this is the helium nucleus, and that can be denoted as 2He4. So let's look at this, the generalized statement. So in an alpha decay, if I write a general statement, it should be look like this. The ZX would be the my parent nuclei and will give me a Z minus 2 Y A minus 4. An element would be changed as it is change in the atomic number and change in the atomic mass. Plus 2He4, this is the helium particle, plus Q. I hope this is clear. Yes, where Q is the energy released. Q is the energy released in the process. If I want to calculate a Q value or energy release, then I can have this relation, that is equals to mx minus of my minus of mass of the helium particle multiplied by c square. This is the Q value, it's an mx minus my minus mhe into c square. Yes, I hope this is clear. Is it clear? Is it? So let's have a look, one more question. The daughter nuclei and the alpha particle are collectively known as the decay products, and let's say this would be the case of uranium. It's a 92U238 will give us alpha particle. Then this, its atomic number has been changed by the 2 and atomic mass has been changed by the 4, and the number of nucleons are always conserved. Yes, you can see this, that this is the 238 as an initial, this is 234 plus 4, even this is 92, this is 90 plus 2. So the number of protons and neutrons are separately conserved. I hope this is clear. So you must be you must be very much aware with this, that when and when alpha particle would be emitted, that will give us a new element which is having two less atomic numbers, and which must be having a 4 less atomic mass, and helium particle will be released. I hope this is clear. Is it is it great? So can you do one of the question based on this? Let's say suppose we have certain element, and that is the 92 uranium 235, and alpha particle has been emitted. Next element is required. Next time 2 alpha particle has been emitted, and again next particle is required. So this is the requirement. So what I should do this, that this is the atomic number and this is the atomic mass. If one of the alpha particle would be released, then my standard relation tells me it's a zxa will be the z minus 2 y a minus 4 plus 2 he4. Yes, here I am interested in only the element, so this atomic number would be decreased by 2. So 92 minus 2, it's a 90. We don't know the element, it's an x. 235 would be decreased by 4, it's a 231. Yes, now 2 alpha elements has been decayed from this. So if 2 alpha elements has been decayed from this atomic number should be reduced by 4. So this is 90, this should be 86, and this is y. And as it was reduced by 4 for the 1 alpha decay, but this is the decay of 2 alpha elements, so it's a decayed by 4. 4 2s are 8, sorry, 231 minus of 8, it's a 223. Yes, this would be the correct answer. And believe me, this kind of question has been asked in the NEET examinations. Yes, even this time JE has certain set of JE have asked this. So please be very careful with this. I hope this is clear. So are you clear with the alpha decay? Are you? Great. Now let's move to the beta decay. We can say that beta particles are nothing but the electrons, and hence the atomic number of the nucleus is increased by 1 unit, and the mass number does not change. In general form of beta decay, that could be written as ZAP, will give us, this is parent nuclei, will give us Z plus 1 daughter nuclei plus minus 1 into e to the power 0. Yes, so this is minus 1 e0. So if it was the case of 90 thorium 234, then this will 91 Pa 234 plus minus 1 E0. So for beta decay, a neutron transforms into a proton within the nucleus according to the equation. And emission of an electron or positron by a nucleus is what we call as the beta decay. So if in beta decay an electron is emitted by the nucleus, and beta plus decay a positron is emitted by the electrons. I hope this is clear. So if I want to write down the general relation, let's first write down for the beta minus decay. So if it was the case of the beta minus decay, then it should be a ZXA will give us. You must always remember this, such as that when it is a minus of decay, it will release a minus 1 E0. So to make this minus 1 E0, this must be Z plus 1 Y A. I hope this is clear. So this is Z plus 1 minus 1, this is Z. Yes, absolutely correct. Plus certain antineutrinos plus Q. I hope this is clear. Is it clear? And if I want the Q value, then Q value of this will be the mass of the ZXA minus mass of the Z plus 1 YA multiplied by C square. This is the Q value. Yes, I hope this is clear. And one more thing you must remember is beta minus decay occurs with with nucleides for which N by Z ratio is too large. N by Z ratio is too large for stability. So beta minus decay occurs with nucleides for which N by Z is too large for stability. Please do remember this. Now let's discuss what would be the situation with beta plus decay. So if I write down the generalized term, then it would be the ZXA. Now it's a beta plus decay, so what I want 1E0, so I need to reduce this. It's a Z minus 1 YA plus 1E0 plus a certain neutrinos plus Q value. So the Q value of this relation could be given as it's a mass times of ZXA minus M into Z minus 1 YA minus 2 into mass of the electrons multiplied by C square. This would be the relation and this would be the situation. Yes, I hope this is clear. Is it clear? Is it? Great. Now one more thing that beta plus decay occurs only when N by Z is too small for stability. I hope this is clear. Is it clear? Is it? So are you clear with beta plus and beta minus? Yes, if beta plus would be there, you need to release 1E0, which we call as a positron. And if beta minus is there, we need to release with the electron. It's a minus 1E0. I hope this is clear. Yes? Great. So can we have one of the question based on this? Now we are going to mixing it with alpha and beta both. So let's say if this was the element 60x, I'm taking the random element which is 120 and alpha particle has been emitted. Next particle is required, then beta minus is emitted and the next element is required, then beta plus is emitted and then next element is required, and then again alpha particle is emitted and that next element is required. So this is the requirement. How will you do this? So this is the 60x 120 and if alpha particle has been emitted, this is 2He4 would be reduction, so this is 58y. This is 120 minus of 4 which is 116. Next a beta minus has been emitted. When beta minus is emitted, the mass number remains the same but the atomic number remains atomic number will be changed, and as I need to release minus 1E0, I need to add 1. It's a 59 Z116. Great. Next what I want the beta plus to be emitted. When beta plus is to be emitted, I need to release 1E0. Yes, so again it would be a 58Y116. Now again alpha particle, from this it's an again alpha particle is emitted, so it's a 2He4, so this is 54Z112. or I should say I should give it a new name. It's a 54W112. I hope this is clear. So can you do this kind of questions? Can you? Are you sure? Great. So now let's switch to the gamma decay. Gamma decay produces a photons for us, and the decay of the gamma uses the following pattern. So parent nuclei would be there. It will give us the daughter nuclei plus the gamma ray. And the example of a nuclear decay that produces a gamma ray is the 91Pa234 will give me a 91Pa234 plus gamma. Surprisingly, you can see this, there is no change in the atomic number, there is no change in the atomic mass. Yes, so nothing has been changed. It is just the released of an energy when electron jumps off from one level to another level, when one energy level to another energy level. So when an excited nucleus transmits to a state of lower energy, it emits gamma ray, and this process is what we call as the gamma decay. And this emission of gamma rays from the nucleus does not alter either atomic number Z or the mass number A. So basically, if I write down the generalized statement, it would be the ZXA will give us ZXA plus gamma. I hope this is clear. Is it clear? Is it? Is it? Are you sure? Great. And Q value for gamma is the 0. Yes, because no mass has been changed. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Great. So now we understood what alpha, beta and gamma emission is. Yes. Now let's discuss about them certain details about the alpha, beta and gamma particles. So it's an alpha. This is about beta. This is about gamma ray. Yes. First, let us discuss about their penetrating power. Let's talk about the penetrating power. Let's say this is alpha contains a penetrating power of x. Then beta contains this as an 100x. And this gamma rays contains it's a 10,000 into x. This is the penetrating power. Let's discuss about their ionizing power. Their ionizing power. So if alpha contains ionizing power of x, then beta contains an ionizing power of 100x. Then the alpha contains an ionizing power that is of 10,000x. Yes, this is the ionizing power. Let's discuss about the charge they contains. So charge, alpha particle, it's a plus 3.2 into 10 to the power minus of 19 coulomb. A beta particle, it's a minus of 1.6 into 10 to the power minus of 19 coulomb. And the gamma particle, the charge will be the 0. Yes. If we talk about the rest mass, of this particles, then rest mass of alpha particle, it's 6.6 into 10 to the power minus of 27 kg. For beta particle, this is equals to 9.1 into 10 to the power minus of 31 kg. And the rest mass of the gamma particle is 0. Please do remember this data. Yes, because they have capability to be asked. Yes. Now let's discuss some more detail. Yes, we have discussed something. So this is the properties. These are for the alpha rays, beta rays and gamma rays. Their origin, all of them has been originated from the nuclei. Their nature, if it is an alpha particle, it is of helium nuclei. Beta rays, they are the fast moving electrons, and the gamma rays, they are the electromagnetic radiations. If I talk about the charge that we have already discussed, it's a plus 2 into E. This is minus of electron and this would be the 0. Our rest mass, it's a 4 times the mass of proton. Our beta rays, it's a mass of the electron, and for the gamma rays, it's a 0. Their speed, it's about 10 to the power 7 meter per second. If I talk about the alpha rays, if we are talking about the beta rays, it is 2.9 into 10 to the power 8 meter per second. And for the gamma rays, it is just as the equal to the speed of light. We have already discussed relative ionizing power. We have already discussed the relative penetrating power. If we discuss about the effect of electric field and magnetic field, then let's first discuss about the effect of the electric field. If it was about the alpha rays, then this will deflect it towards the negative plates. If it was about the beta rays, then they will deflect it towards the positive plates. And if we talk about the gamma rays, they are undeflected. Let's discuss about the effect of magnetic field. If it was alpha rays, it was deflected. If beta rays, even this will be deflected in magnetic field, and in the gamma rays they are the undeflected. Yes, so this is the range in the air and fluorescence. Yes, so please try to remember this, and this will help us a lot to get or to clear the questions. I hope this is clear. Is it clear? Now let's look at certain quick questions. When an excited nucleus transits to a state of lower energy, it emits gamma ray, and this process is known as the gamma decay. Yes, this would be the correct answer. Next, emission of an electron or positron by a nucleus is what we call as this is what we known as the beta decay. I hope this is clear. Is it clear? Is it? So do you have any doubts? No? Great. Now let's discuss about the radioactive low or the radioactive disintegration. So basically it is the rate of disintegration of atoms at any instant is directly proportional to the number of atoms present at that instant. So activity A would be equals to number of disintegration per unit time, and that is what we denoted it by dn by dt. That should be equals to lambda into n, where this n, capital N, is the total number of nuclei, and lambda is the decay constant, or what we can say it's a disintegration constant, and that depends on the nature of the element. So basically the law is this: it's a dn by dt. Its rate of disintegration is directly proportional to the number of active nuclei present in the sample. So if I remove this proportionality symbol, this will be seen as dn by dt, which should be is equals to minus of lambda into n, and this negative sign indicates that as time increases and decreases and so on. I hope this is clear. So as we understood that n, that would be equals to total number of moles multiplied by Avogadro number, and to find out the total number of moles, we are having it's an m by m multiplied by Na, which is equals to weight in gram divided by molecular weight multiplied by Avogadro number. So unit of lambda is the second inverse, and if nt is the number of atoms at any instant t, and n naught is the number of atoms at t equals to 0, then this n of t would be equals to n naught into e to the power minus of lambda t. Yes, so from the decay law we have this relation, that is dn by dt is equals to minus of lambda n, which can be written as dn by n, that is equals to minus of lambda into dt, and this negative sign indicates that total number of active nuclei remain in the sample is keep on decreasing. So if I integrate and taking the limits, this is equals to integration of dn by n minus of integration of lambda dt. From when it's a 0 time, it's a n naught number of samples; when it's a t time, it's an n of t. So if it is integration of dn by n, it's an ln n from n naught to the nt minus of lambda into t to the 0. So this is ln n t minus ln n 0. This is equals to minus of lambda into t. So this is ln nt by n naught is equals to minus of lambda t. So this could be written as nt by n naught, which is equals to e to the power minus of lambda t, or this could be written as nt is equals to n naught into e to the power minus of lambda t. Yes, number of nuclei present at any point of time would be equals to initial number of nuclei present in the sample multiplied by e to the power minus of lambda, which is a decay constant, multiplied by time t. This is these are the graphs that we have plotted it for different y and z x axis. First graph is about number of undecayed nuclei. Yes, they are the number of sorry, they are about the number of undecayed nuclei. This is n naught, this is time, and if you look at this graph is keep on decreasing. Yes, next it is about the number of nuclei. It's a number of nuclei versus time. Yes, so this is about the daughter nuclei, and this is keep on increasing, and this is about the parent nuclei. And if I plot a graph for the log of n naught for this time, it would be a straight line. Yes, but with negative slope. So this shows that radioactive nuclei decreases exponentially. This radioactive nuclei will be decreases exponentially with the time. I hope this is clear. Is it clear? Let's already talk about the activity. So whatever the decay rate is what we call as the activity or rate of activity, generally denoted as R, which is equals to mode of dn by dt, or we can say it's a lambda into n. So this could be written as it's a lambda into n naught into e to the power minus of lambda t, or that could be equals to a naught into e to the power minus of lambda t. So this is the relation, which is R is equals to R naught into e to the power minus of lambda t, where R naught is the rate of decay at t equals to 0, and R is the rate of decay at time t equals to t. SI unit of activity. SI unit of activity is the becquerel, and the other units are the Curie or Rutherford. Yes, and you must remember this, that one becquerel, it's a one disintegration per second. Same way one Curie, it is the 10 to the power 6 disintegration per second, or one Rutherford, it's a 3.7 into 10 to the power 6 disintegrations per second. I hope this is clear. Is it? Is it clear? Great. So basically this is the situation that any radioactive element takes infinite time to disappear completely. So it is useful to speak about the half-life period of the element. Yes, we always calculate the half-life of the time, because maybe any element takes infinite amount of time to completely disappear itself. So to calculate the half-life, we will look at this. We will go through the situation. It's a half-life period. So let's look at this. So individual nuclei decay take place at the at the random times, and this randomness is a feature of the quantum theory, and the probability for decay can be given specified in terms of the half-life of the given nucleus. So let's assume that initial number of nuclei, which we call as an n naught, is present in a sample at t is equals to 0, and at time t is equals to t, half of the nuclei will get decayed. So if we plot this graph, let's say total number of active nuclei at 0 seconds will be equals to n naught, and at t equals to t it is keep on decreasing. So you can see this is n naught to n naught by 2. This is first half. This is n naught by 2 to n naught by 4. This is second half. This is n naught by 4 to n naught by 8. This is third half. This is n naught by 8 to the still keep on decreasing, it is probably n naught by 16. Yes, this is fourth t half. So this is how my elements will keep on decreasing. So half-life period is defined as the time taken by any nuclei to disintegrate to half of its original number of nuclei. So when t is equals to t, then n would be equals to n naught by 2. So according to the radioactive decay law, what we can give is the n is equals to n naught into e to the power minus of lambda into t. And as we understood that this will become the half, it's a n naught by 2, which is equals to n naught into e to the power minus of lambda t. So this is equals to 1 by 2 equals e to the power minus of lambda t. So this is equals to e to the power minus of lambda t is equals to 2, or we can say it's a, if I take a log on both the sides, it's a lambda t is equals to ln 2. So this t would be equals to 2.303 into log 2 divided by lambda. So this is t, or generally certain authors denoted is it as a tau. Yes, this is what it pronoun, it's a tau. It's a 0.693 by lambda, where lambda is the decay constant. First we will see the formula of the average life, and then we will switch to the numericals based on all of this. So let's first discuss about the average life period. Average life period can be defined as the ratio of the total lifetime of all the n nuclei to the total number of original nuclei n naught. So this mean life would be equals to total lifetime of all atoms to the total number of atoms. So this is tau, which is integration from 0 to infinite, it's a t dn by an, and this is equals to dn by dt, which should be is equals to minus of lambda n. So this dn would be equals to minus of lambda n into dt. But we understand that n is equals to n naught into e to the power minus of lambda t. So this is equals to dn is equals to minus of lambda into n naught into e to the power minus of lambda t into dt. So if I took an average of this and simplify this, we are having this, it's a tau, which is equals to 1 by lambda. Or if I want to compare it with the half lifetime, then that would be equals to 1.44 t, or we can say it's a t divided by 0.693. I hope this is clear. Is it clear? Great. Let's look at certain quick questions. Lambda is known as the, yes, lambda is the decay constant. Next, half-life period tau half. Half-life period tau half could be given as it is equals to 0.693 divided by lambda. This is the tau half. I hope this is clear. Is it clear? So do you have any doubts up till now? Do you? No? So are you ready for the question? Are you? Great. Let's have a look. Suppose I have been given that a radioactive isotope, a radioactive isotope has a half-life of 5 seconds at t equals to 0. A given sample has 8,000 atoms. Calculate first decay constant, second average life, next time t1 when 1,000 atoms will remain in sample, and next number of decays, number of decays per second at time, at time t is equals to t1. So first go through the data very carefully and then let me know how will you do this. Have you gone through it? So what all they have given? They have given that a radioactive isotope has a half-life of 5 seconds. So let me write down this. It's a tau half, which is equals to 5 seconds. At t is equals to 0, a given sample has 8,000 atoms. So it's an n naught is given, which is equals to 8,000. So first, let's do it. It's a decay constant is required. First, it's a decay constant, that is the lambda is required. How shall we do this? So as we understood that it's a tau half, which is equals to 0.693 by lambda, and from this is the lambda, which is equals to 0.693 divided by tau half. So this is equals to 0.693 divided by 5 as it is given. So this is equals to second inverse. So our first task has been done. Yes. So next, it's a mean life or average life. How will we do this? As we understood that this is t average would be equals to 1 by lambda. Yes. And this should be equals to 1 by, it's a 0.693 divided by 5 seconds. This is 5 divided by 0.693 seconds. I hope this is clear. So this has been done. Next is the time t1 when 1000 atoms will remain in the sample. It's a t is equals to t1 when n would be equals to 1000. So how will we do this and what can be done? What can be done? Think over it and let me know. So any idea? How will we do this? How will we do this? That 1000 atoms should remain in the sample. So if you understood this logically, then initially it was the 8,000 samples were there, and we have a concept of half-life time. Yes, that total number of samples will become the half of the initial. So initially it was 8,000. Then at certain time it would be a 4,000. It's 8,000 divided by 2. Then it's a 4,000 divided by 2, which is 2,000. And from this 2,000, it has become the 1,000. So from 8,000 to 4,000, it has taken one of the half-life time, which is of 5 seconds according to the R data. Let's look at this as half-life time is the 5 seconds. So from this to this, again 5 seconds would be there. From this to this, it's again 5 seconds would be there. So total 15 seconds are required to to decay it and to initial samples from 8,000 to reach at the 1,000 seconds. So it is our third question where they have asked about the time t1 when 1,000 atoms will remain in sample. Yes, I hope this is clear. Now this is the simplest approach because this is the 8,000, 4,000, 2,000, 1,000. But if the data is very large, how will we deal with this? So for that we have very simple construction. It's a n by n naught, which is equals to 1 by 2 to the power n. Yes, where this n is the number of times of life achieved, and to get the total time we should have this. It's a t is equals to n into tau. So in our case, let's check this. It's n would be equals to 1,000 divided by n naught, which is equals to the 8,000. This is equals to 1 by 2 to the power n. As you can see, this is 1 by, which is equals to 1 by 2 to the power 3, which is equals to 1 by 2 to the power n, and this
this is simply n equals to 3. So the total time would be equals to 3 into 5. This is 15 seconds. So please do remember this. This is very helpful relation. And with the help of this, we are going to get this very fast. Yes. So n by n naught, it's a 1 by 2 to the power n. Please do remember this. Now, even one of the question has been remained, that is the number of decays per second at a time, which is equals to t is equals to t1. So I want that. Let's have a look. How will we do it? Basically, they have asked a rate of decay, or I should say it's a dn by dt. And that dn by dt will be lambda into n. The lambda, the lambda was 0.693 by tau half. 0.693 by 5 multiplied by 1000. Yes, it was thousand atoms was present in that sample. So this is 5 multiplied by 200, and the rest of the thing, it's, you can do this. It's a second inverse. I hope this is clear. Is it clear? Is it? Are you sure? Do you have any doubt in this? Is there anything? No? Great. Now let's look at the next question. Suppose they have asked that the half-life of certain material is 4 days. Calculate how much of 15 into 10 to the power minus of 3 milligram of that element will remain after 4040 days. So go through the data first. What they have given. They have said that half-life of a certain material is 4 days. So it's a tau half. It is equals to the 4 days. And a initially the element is it's an 15 into 10 to the power minus of 3. You can write this as an m naught as well. And at what time they want this? It's after 40 days. So t is equals to 40 days. So according to the R relation, we can have this. It's a t is equals to n into tau half. This is 40. This is equals to n. This is equals to 4 days. Okay. So this is equals to 4. So we can have it's an n equals to 10. So it has been passed. It has been passed through the 10 half-life cycles. So basically it's an m by m naught, which should be equals to 1 by 2 to the power n. It's an m, which is equals to m naught into 1 by 2 to the power 10. And this n naught would be equals to 15 into 10 to the power minus of 3. 1 by 2 to the power 10. It's gram. This much will be available in the sample. I hope this is clear. Yes. Is it clear? Is it? So do you have any doubts? Do you? No? Great. Are you ready for the next question? Are you? Are you Let's look at the next question. Ready? Are you done? Great. So now let's look at the next question. Suppose they have asked us that if a radioactive material, if a radioactive material remains 25 percentage after 16 days, lifetime will be? This has been asked. How will you do this? How will you do this? What is to be done? What they have given is that a radioactive material remains 25%. So basically, it's an n by n naught, which is equals to 25 out of 100. And they want this after 16 days. This happens after the 16 days. So they want to find out the half-life time. It's the tau half that is required. What we understood is this is n by n naught, which is equals to 1 by 2 to the power n. This is equals to 1 by 2, which is 1 by 2 to the power n. So this n equals to 2. Yes. So this is T is equals to n into tau half. Total time it's the 16 days into 2 into half. So tau half will be equals to 8 days. This amount of time has been taken. This amount of time has been taken to achieve this. I hope this is clear. Is it clear? Correct. Now there are certain questions which there are the questions of parallel disintegration. When we say parallel disintegration, the situation will be, let's suppose this is the sample, and from this sample a certain element has been emitted, or it's a decayed by an disintegration constant lambda 1, and certain other elements simultaneously decay with lambda 2, and I have been asked everything about that sample. What we can do is we understand this lambda 1 is equals to lambda 1 by lambda 1 plus lambda 2. And we also know that this is the tau half, which is equals to 0.693 by lambda. So from the lambda, it's a 0.693 by tau half equals to 0.693 by tau half of first element plus 0.693 by tau half of second element. So this is the tau half of the system, because this two elements has been decayed simultaneously. Here we can add this average level. It's a P average, because it is a one time increase. Yes, we can have P average of first element increase multiplied P average of second element. Please note this part. Please note this part. And we will use this in the next question. is equals to 1 by tau half of 1 plus 1 by tau half of second. So this is 1 by 10 plus 1 by 20. This is 2 by 20 plus 1 by 20. And this is equals to 1 by tau half, which is equals to 2 by 20 plus 1 by 20. This is 3 by 20. So this tau half of the system will be equals to 20 by 3 seconds. I hope this is clear. And initially this contains 8,000 atoms, and now they want that at which time it will be remain only 500 atoms in the sample. So we are doing the same thing. It's n by n naught is equals to 1 by 2 to the power n. This is equals to 500. This is equals to 8,000. This is equals to 1 by 2 to the power n. This has gone, this has gone, this is by 16. So this is 1 by 16 is equals to 1 by 2 to the power n. And from this, n which is equals to 4. So if it is n is equals to 4, this should be p equals to n into tau. Yes. So what amount of time is required? This is equals to 4 cycles are required, and tau of is 20 by 3 seconds. So this is 80 by 3 seconds are required to make this happen. I hope this is clear. Is it clear? Is it? Great. So let's wind up this session over here. This was all about the radioactivity of a nuclei. Please go through this kind of questions and many more questions that has been given in your practice modules. So please go through it. This will help us to get the good numbers. Thank you. Have a good day. Bye bye. Take care.